Hello there, and welcome to the Sleep Port. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring the universe itself. Not just one galaxy or star, but the vast, expanding whole. We'll move gently from fact to fact, learning about black holes, ancient light, dark matter, and distant galaxies. Some things may surprise you. Others may stay with you like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. The universe might be older than we thought. Most current estimates place the age of the universe at about 13.8 billion years. This number is based on measurements of the cosmic microwave background and how fast the universe is expanding. But not every approach lines up. Certain observations of very old stars and distant galaxies imply ages that push beyond what that estimate permits. Others challenge the assumed expansion rate or propose that dark energy itself may be evolving over time. These tensions remain unresolved, and most astronomers continue to accept the 13.8 figure. Still, the questions persist. Could the universe be older? Did we overlook something fundamental? It is possible that what we call the beginning was only one chapter in a much longer, stranger narrative. There are also countless rogue planets drifting through space without stars. Not all planets circle suns. Some are entirely unbound, wandering the galaxy alone, with no star to warm them or illuminate their skies. These rogue planets may have formed normally, then ejected from their star systems by gravitational chaos. Others might have formed on their own, like failed stars. They're dark, cold, and nearly invisible, unless they pass in front of background stars or glow faintly in infrared. Astronomers estimate there may be billions of them in the Milky Way, perhaps even more than the number of stars. Each one is a silent world, adrift in darkness, spinning alone in the vast spaces between. No sunrises, no sunsets, just endless night broken only by distant starlight. The universe may recycle itself through infinite cycles. The standard model of cosmology describes a universe that began with the Big Bang and will continue expanding, possibly forever. But some theories imagine a different story, one where the universe goes through cycles of expansion and collapse. In these models, the universe doesn't end with a cold fade or a final crunch. Instead, it resets. After reaching a certain point, it might bounce, collapsing inward, then rebounding into a new expansion. Each cycle could wipe away the old structures, but preserve subtle traces of what came before. These ideas are speculative, but intriguing. They suggest that the universe may have no true beginning or end, just a rhythm stretched across unimaginable spans of time. One universe giving rise to another, over and over again. The oldest light we can see comes from 380,000 years after the Big Bang. Before that moment, the universe was a glowing fog, so hot and dense that light couldn't travel far without scattering. But as it expanded and cooled, it reached a turning point. Atoms formed, the fog cleared, and light was suddenly free to move. That ancient light is the cosmic microwave background, and we can still detect it today. It's the oldest direct signal in the universe, not from stars or galaxies, but from the universe itself, when it was just beginning to become transparent. The photons we observe now have been traveling for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. This light is faint but ever-present, a quiet glow that carries the memory of the universe's earliest clarity. Some stars have planets made almost entirely of diamond. In certain solar systems, the chemistry is very different from ours. If a planet forms with more carbon than oxygen and the pressures are high enough, something remarkable can happen. A diamond planet. Astronomers have discovered at least one such candidate, a dense world orbiting a pulsar, likely the remnant of a dead star. Based on its mass, density, and composition, the entire planet may be a crystalline form of carbon, essentially a giant diamond. It's far too hot to sparkle, and it wouldn't look like a jewel up close. But deep beneath the surface, immense carbon lattices could stretch for thousands of kilometers. These strange worlds aren't common, but they remind us how diverse the universe can be. A planet made of rock, a planet made of gas, and sometimes a planet made of crystal. The universe may have no edge, just endless curvature. It's tempting to imagine the universe as something with an edge, a border we could reach if we traveled far enough. But space doesn't seem to work that way. According to general relativity, the shape of space is determined by its contents, and current evidence suggests that the universe is either infinite or so vast and curved that it loops back on itself. If that's true, you could, in theory, travel in a straight line forever and eventually return to where you started. Not by hitting a wall, but by wrapping around curved space. This is similar to how traveling around Earth doesn't reveal an edge, just a globe. The universe may work in the same way on a much grander scale. Not infinite in space, but infinite in journey. The Sun once had a twin, and it may still be out there. Some astronomers believe that our Sun was born with a twin, a companion star formed from the same cloud of gas and dust over 4 billion years ago. Many stars forming pairs, and there's no reason to think our Sun was an exception. If it existed, this lost sibling would have drifted away long ago, pulled apart by the slow gravitational tug of the Milky Way. It might still be out there, orbiting the galaxy on a different path, invisible to us now. Some theories even link this twin, nicknamed Nemesis, to mysterious extinction patterns on Earth, though there's no solid evidence for that. Still, the idea lingers that our Sun, steady and alone in our sky, may once have shared its birth with a silent partner, long vanished into the stars. A raindrop of neutron star would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, incredibly dense remnants left behind after supernova explosions. They're only about 20 kilometers wide, but their mass is greater than the Sun's. The matter inside is so densely packed that a single teaspoon of it would weigh billions of tons. If you imagined a single raindrop of neutron star material, it would be heavier than any mountain on Earth. That kind of density defies our everyday experience. Atoms are crushed together so tightly that electrons and protons merge into neutrons, forming a kind of superfluid neutron soup. Neutron stars are extreme objects, small, dark, heavy, and spinning rapidly. But in their quiet mass, they hold the memory of stellar collapse, a final state where matter becomes nearly pure gravity. Light from one galaxy can reach us from multiple directions. Sometimes light doesn't travel in a straight line. In regions of space where gravity is especially strong, near massive clusters of galaxies, for example, space-time itself curves. This curvature bends the path of light, like glass bending a beam. It's called gravitational lensing. And one of its strangest effects is that we can sometimes see multiple versions of the same distant galaxy from different angles. These images can appear as arcs, smudges, or even complete rings. They're not duplicates in space, but duplicates in vision. Different paths that light is taken through warped space-time to reach our eyes. In a few rare cases, astronomers have observed the same supernova explode more than once as its light arrived through different gravitational routes. It's a quiet reminder that in the universe, even light can get lost, take a longer path, and still find its way home. The first stars may have burned 1,000,000 times brighter than the sun. The very first stars were unlike anything we see today. Born from the pure hydrogen and helium left after the Big Bang, these stars, called population the third stars, likely formed with no metals at all, making them massive, hot, and short-lived. Some may have been hundreds of times the mass of the sun. They would have burned through their fuel quickly, shining 1,000,000. And as Earth moves through this halo, trillions of dark matter particles are thought to pass through every square centimeter of your body each second. They don't collide with your atoms. They don't leave a trace. But they're there, ghost-like, ever-present, and essential. Without dark matter, galaxies wouldn't hold together, cosmic structures wouldn't form, and the universe would be very different. We still don't know what dark matter is made of, but we know this much. It's part of your world, passing through you silently and continuously, even as you sleep. Some galaxies glow without any stars inside. In the quiet reaches of the universe, astronomers have discovered galaxies that shine but barely contain any stars. These ghostly systems are full of gas and dark matter, but show little to no evidence of star formation. Some may have lost their stars in violent gravitational encounters. Others may never have made many stars at all. A few are nearly invisible except in certain wavelengths of light. Faint smudges in deep surveys of the sky. These galaxies challenge what we thought we knew about how galaxies form and evolve. If they're rich in dark matter, why haven't they built stars? If they had stars once, where did they go? These dim, quiet systems float through space like forgotten bones of cosmic history. Remind us that not every galaxy is filled with blazing light. Some simply drift unseen and unanswered. The universe has a cold spot that shouldn't exist. In the cosmic microwave background, the faint glow left over from the Big Bang, there's a patch of sky that's unusually cold. It's not just a little cooler than its surroundings, it's significantly colder and much larger than scientists expected. This cold spot spans hundreds of millions of light years, and its presence doesn't quite match the smooth randomness we'd expect from early universe physics. Some think it may be the imprint of a vast cosmic void. Others wonder if it could hint at something even stranger, like the collision of our universe with another in the very early moments of inflation. No explanation so far fully fits. The cold spot remains one of the most quietly unsettling puzzles in cosmology. Not a screaming anomaly, but a whisper that something about our universe may not be what it seems. The moon is slowly leaving us behind. Every year, the moon drifts a tiny bit farther away from Earth, about 3.5 centimeters. That's roughly the rate at which your fingernails grow. This slow retreat has been happening since the moon formed around 4.5 billion years ago. Back then, it was much closer, and a day on Earth was just a few hours long. The cause is tidal friction. As the Moon pulls on Earth's oceans and Earth spins beneath them, a small transfer of energy gradually pushes the Moon outward in its orbit. It's a quiet, relentless process, invisible on human timescales, but unmistakable over eons. In the far future, Earth and the Moon may become tidally locked, always showing the same face to each other. For now, it just keeps slipping away, little by little, as we spin beneath its distant, glowing light. Binary stars can swap their outer layers like dancers in contact. In some binary star systems, the two stars orbit so closely that their outer layers begin to touch. As they evolve, one star can swell and spill matter onto the other, creating a delicate, spiraling exchange of material. Sometimes the transfer is calm and steady. Other times it triggers bursts of light, rapid rotation, or even a complete merger. The physics is complex, but the image is oddly graceful. Two stars locked in orbit, spinning close enough to brush and blend. One star may end up stripped to a glowing core, while the other becomes swollen and enriched. Their fates are bound together. Some of the most unusual objects in the universe, like certain supernova or compact neutron star pairs, begin as these quiet, touching binaries. A reminder that in space, even stars can share, change, and sometimes embrace. The vacuum of space is not truly empty. Even in the deepest, darkest reaches of space, far from any star or galaxy, the universe is never truly empty. According to quantum physics, what we call vacuum is a sea of activity. Tiny particle-antiparticle pairs blink into existence and vanish almost immediately. These quantum fluctuations happen all the time, everywhere, creating a kind of restless background to reality itself. They can influence the motion of particles, affect the behavior of fields, and even contribute to the energy of empty space. This is part of what gives rise to dark energy, the mysterious force accelerating the expansion of the universe. So when we picture deep space as silent and still, that image is only partly true. Beneath the quiet lies a dance of probabilities, a hidden hum of creation and disappearance, always just below the surface of nothing. Time may flow at different rates in different regions of the cosmos. We think of time as steady, a ticking rhythm that flows the same for everyone, everywhere. But in reality, time is deeply linked to gravity, motion, and the shape of space-time itself. In regions where gravity is strong, like near a black hole or a dense galaxy cluster, time slows down relative to places where gravity is weaker. This isn't just theory. It's been confirmed by experiments, satellites, and atomic clocks. But some cosmologists wonder whether time could also vary on even larger scales. Could different parts of the universe experience time at slightly different rates due to how the universe expanded in its early moments? The idea is speculative, but it opens strange possibilities. In a cosmos governed by relativity, even time may not be absolute. It may stretch, slow, or bend, quietly shaped by the space through which it flows. The Milky Way has a hidden halo that's larger than the visible galaxy. When we look at images of the Milky Way, we see a glowing spiral, stars, dust, and gas arranged in beautiful arms. But surrounding this familiar structure is something vast and mostly invisible: the galactic halo. It's a huge sphere of diffuse gas and dark matter that extends far beyond the visible edge of the galaxy, reaching distances many times greater than the span of the disk itself. This halo contains ancient star clusters, stray stars, and vast amounts of unseen mass. It's held together by gravity, shaped by the history of collisions and mergers, and plays a quiet role in the galaxy's stability. Though we can't see it directly, we infer its presence through the motion of stars and the bending of light. The Milky Way, it turns out, is just the bright center of something much larger, a glowing heart wrapped in invisible arms. We've detected light from a galaxy just 200 million years after the Big Bang. The universe is about 13.8 billion years old, but light doesn't travel instantly. It moves through expanding space, stretched and slowed along the way. That's why we can see galaxies not as they are, but as they were long ago. Recently, astronomers using the James Webb Space Telescope identified light from a galaxy that existed just 200 million years after the Big Bang, a blink of time on the cosmic scale. That light has been traveling toward us for more than 13.5 billion years. The galaxy itself is small, faint, and primitive, but it holds clues to how the first structures formed. Observing it is like looking through a narrow window into a world we were never meant to see. The universe in its earliest chapters, when darkness was just beginning to give way to stars. The large-scale structure of the universe looks like a neural network. When astronomers map the positions of galaxies across enormous distances, a surprising pattern emerges. Galaxies aren't scattered randomly. Instead, they cluster together along thread-like filaments with vast empty regions, cosmic voids in between. This interconnected web stretches across billions of light years and is sometimes called the cosmic web. What's eerie is that when you zoom out far enough, this structure looks uncannily like a neural network, the kind found in the human brain. Dense nodes of galaxies are like neurons, and the filaments are like axons connecting them. Of course, the resemblance is purely structural. The universe isn't thinking, but it's still quietly beautiful to consider. The largest structure we know, and the one inside your own mind, shaped by entirely different physics, can end up looking so strangely alike. Stars can sing through the vacuum of space. There's no air in space, so we don't hear sound the way we do on Earth. But stars still make sound. Deep, slow vibrations that travel through their interior gases like seismic waves through a planet. These pressure waves make the star pulse and oscillate, and scientists can detect them by observing tiny changes in the star's brightness or surface motion. The field that studies this is called astroseismology, literally the seismology of stars. Each star has its own internal frequencies, like a fingerprint determined by its size, structure, and age. By listening to these stellar vibrations, scientists can peer inside stars and learn what's happening beneath the surface. It's a kind of cosmic echolocation, a way to hear the music of stars across light years, even if the song is silent to human ears. Some stars are older than the galaxies they live in. Galaxies are not built all at once. They form over time, merging with smaller systems and drawing in stars and gas from other regions. That means some stars inside a galaxy can be older than the galaxy's current structure. They may have formed in earlier, smaller galaxies that later merged into a larger one. These ancient stars often live in the outskirts or in globular clusters, tightly bound groups that orbit far from the galaxy's core. Some of them are over 13 billion years old, nearly as old as the universe itself. They carry the chemical signature of a much younger cosmos when there were fewer heavy elements and only the simplest atoms. These stars are like fossils, quiet survivors from before the galaxy fully came together. Their light is old. Their stories began before much of what we know had even formed. There are galaxies without dark matter, and we don't know why. Dark matter is thought to be the invisible glue holding galaxies together. It explains why stars in the outer regions of galaxies move faster than expected, and why galaxies cluster the way they do. But in the last few years, astronomers have found galaxies that seem to defy this rule. Galaxies that behave as if they have no dark matter at all. Their stars move as if only the matter we can see is there. The finding came as a surprise and does not sit comfortably within existing models. Some researchers suggest the dark matter may have been torn away during ancient collisions. Others suspect that our understanding of dark matter itself is still incomplete. Either way, these unusual galaxies hint that the universe still holds hidden layers, and that what we assume to be universal may not apply everywhere. The sun resonates like a vast, resonant bell. Deep within it, sound waves travel through the plasma, reflecting between layers and setting the entire star into a faint, constant vibration. These waves are nothing like the sounds our ears detect. They are pressure waves, slow, deep, and far below the range of human hearing. But with sensitive instruments, scientists can detect them and use them to study the sun's internal structure. This field is called heliosysmology. By observing how the sun rings, scientists can map what's happening deep below the surface, its density, rotation, and even its hidden flows of hot gas. The sun, in this sense, acts like a musical instrument, vast, complex, and always playing. We just need the right tools to listen. And what we hear helps us understand not only the sun itself, but stars everywhere. Galaxies follow filaments made of something we cannot see. The universe's largest structures aren't made of stars or gas. They're shaped by something invisible, dark matter. Over billions of years, this dark matter formed enormous filaments stretching across space. And galaxies tend to form and move along these filaments, like beads on a string. We can't see the filaments directly, but we can infer them by observing how galaxies cluster and how light bends as it passes through these regions. The filaments can span hundreds of millions of light years and connect vast clusters of galaxies. In between lie great voids, merely empty regions where very little matter exists. The dark matter filaments act like a hidden scaffolding for the visible universe, shaping how galaxies grow and where they go. And yet, we still don't know what dark matter is. The structure is there, immense, unseen, and quietly holding the universe together. Space can stretch faster than the speed of light. In normal circumstances, nothing can move faster than light. But space itself isn't bound by that rule. During the early moments after the Big Bang, space expanded so rapidly that regions of the universe were pulled apart faster than light could travel between them. This wasn't motion through space. It was the expansion of space itself. Even today, distant galaxies aren't racing away because they're moving quickly through space. They're receding because the space between us and them is stretching. And if they're far enough away, that stretching makes them recede faster than light, which is why we'll never see them again. It's not a violation of physics, but a quiet consequence of how space behaves on cosmic scales. The universe doesn't need to rush. It simply expands calmly and relentlessly beyond what we can follow. Our solar system moves through space like a helical spiral. It's easy to picture the planets orbiting the sun in neat, flat circles. But zoom out further and something stranger emerges. The sun itself is moving, orbiting the center of the Milky Way at nearly 1,000,000 kilometers per hour. As it moves, the planets follow in tow, not just circling the sun, but spiraling through space behind it. The combined motion creates a helical pattern, like a corkscrew or a twisting ribbon. Everything is in motion: the planets, the sun, the stars, the galaxy itself. There is no stillness in space, only graceful, ceaseless drift. Even as we sleep, we're tracing slow spirals through a galaxy in motion, wrapped in layers of orbits within orbits. A dance so vast, we never feel it. Even nothing has a temperature. If you travel far enough from stars, planets, and galaxies into deep intergalactic space, you'll find yourself surrounded by what seems like pure emptiness. But even the vacuum has a temperature. That temperature is about 2.7 Kelvin, just a few degrees above absolute zero. It comes from the cosmic microwave background, the leftover glow from the Big Bang, now stretched and cooled by billions of years of cosmic expansion. This faint radiation fills the entire universe. No matter where you go, it's there. It's the quiet thermal signature of the early universe, still lingering, still measurable. And in the future, it will cool even further. In a few trillion years, the universe may approach absolute zero, but never quite reach it. Because even in the vastest emptiness, the echo of heat remains. Quantum fluctuations may have shaped the entire universe. At the smallest scales of reality, far smaller than atoms, the universe behaves unpredictably. Tiny, random fluctuations in energy can appear and vanish in an instant due to the uncertainty built into quantum physics. And according to many cosmologists, those brief, random blips may have been magnified during the universe's first moments through a process called inflation. As space expanded at unimaginable speed, tiny fluctuations were stretched to cosmic proportions. Those fluctuations became the seeds of structure, the places where matter would clump, where galaxies would form, where stars would eventually ignite. In other words, the grand structure of the cosmos, the galaxies, the filaments, the voids, may all trace back to fleeting random events at the smallest possible scale. Everything we see today, born from the trembling of nothing. Dying stars can pulse like heartbeats across millions of years. Not all stars end with a bang. Some fade more slowly, and during their final stages, they can pulsate, swelling and shrinking in rhythmic cycles. These stars, called variable stars, change in brightness over time. In some cases, the changes are steady and regular, repeating like a slow heartbeat. The pulses are caused by changes in the star's outer layers, gases expanding and cooling, then collapsing and heating up again. Some stars pulse every few days. Others take months or even years to complete a cycle. These rhythmic stars have been used to measure distances in space since their pulsation patterns relate to their true brightness. They also serve as quiet reminders that even in death, stars can keep time, not with a clock, but with a long, slow breath. Across cosmic ages, Earth is inside a giant bubble of hot gas. If you could see far into the invisible wavelengths of light, past what your eyes can detect, you'd find that our solar system sits inside a vast, glowing bubble of hot gas. It's called the local bubble, and it stretches for hundreds of light years in every direction. This bubble is thought to have been carved out by ancient supernova, exploding stars that blasted shockwaves into the surrounding gas, heating and clearing it out. Now, our solar system drifts quietly through this low-density region, surrounded by a shell of hotter gas and dust. It's not dangerous. It's not something we can feel, but it's there. A kind of quiet chamber around us, born from violence long ago, now part of the gentle backdrop of our galactic neighborhood. There's a vast, empty region behind the Great Attractor. The Great Attractor is a mysterious gravitational anomaly, a region of space so massive that entire galaxy clusters, including our own Milky Way, are slowly drifting toward it. But behind this immense concentration of matter lies something even stranger. A region known as the dipole repeller, where space appears unusually empty. It's not just a patch with fewer galaxies. It's a vast cosmic void stretching for hundreds of millions of light years. And oddly enough, its emptiness seems to push galaxies away. Together, the Great Attractor and the dipole repeller create a quiet gravitational tug-of-war that helps shape the motion of our local universe. We are drawn forward by unseen mass and pushed back by the emptiness beyond. It's a reminder that in the cosmos, both presence and absence can shape the path we follow. Neutrinos pass silently through the Earth and through you. Right now, trillions of particles called neutrinos are passing through your body, and you'll never feel them. Neutrinos are incredibly light, neutral particles produced in enormous numbers by the Sun, exploding stars, and even the early universe itself. They barely interact with normal matter. They can fly straight through a planet or your entire body without leaving a trace. Some pass through detectors buried deep underground, where rare collisions help us study them. But most simply pass through unnoticed. These particles are everywhere all the time, silently streaming through space and matter alike. They move at nearly the speed of light, and yet they almost never touch anything. The universe is full of motion, even when everything feels still. The most massive stars can collapse directly into black holes without a bang. We often imagine the death of a massive star as a violent supernova, a brilliant explosion lighting up the galaxy. But for the most massive stars, the end can be strangely quiet. Some stars are so heavy that when they run out of fuel, their cores collapse inward, and gravity winds so completely, so suddenly, that even the outer layers fall straight in. No explosion, no bright farewell, just a sudden disappearance. This process is called a direct collapse. In the moment, a star is gone, replaced by a black hole, silent, invisible, and crushingly dense. Astronomers have even observed stars that seem to vanish without a trace, as if the light simply blinked out. It's a reminder that not all cosmic endings are fireworks. Some are whispers into the dark. Galaxies can orbit one another like moons around planets. We tend to think of galaxies as isolated islands in space, but many live in small groups where they interact and even orbit one another. Our own Milky Way, for example, has dozens of smaller satellite galaxies. The large and small melanic clouds are the most famous. These companions move around the Milky Way like moons around the planet, slowly tracing long, elliptical paths through space. Sometimes, larger galaxies pull stars from their companions, forming streams and tidal tails that stretch across millions of light years. Over time, a smaller galaxy may be absorbed completely. These cosmic dances happen over billions of years. Slow, graceful interactions on a scale we can barely imagine. In the quiet of deep space, even galaxies can keep each other company. The universe's brightest explosions come from collapsing magnetic stars. There's a rare kind of explosion called a magnetar hypernova, and it may be one of the brightest things the universe can produce. A magnetar is a neutron star with an unimaginably strong magnetic field, trillions of times stronger than Earth's. If a massive star collapses into a magnetar and releases its energy quickly, it can produce a burst of light and energy far more powerful than a typical supernova. These events may be responsible for some long-duration gamma-ray bursts, flashes of high-energy light that travel across the universe and briefly outshine entire galaxies. The explosion lasts only seconds, but its light can reach us from billions of light-years away. It's one of the universe's most intense phenomena, created by a small, dense object wrapped in magnetic fire collapsing in on itself. The edge of the observable universe is not the edge of the universe. When we look out into space, there's a limit to how far we can see. About 46 billion light-years in any direction. That's the edge of the observable universe. It's not a wall or a boundary, just the furthest distance light has had time to reach us since the Big Bang, given the expansion of space. Beyond that, the universe likely continues. We just can't see it yet. And because the expansion of space is accelerating, some parts of the universe are moving away from us faster than light. That means their light will never reach us, not even in infinite time. The observable universe is like a bubble of vision. Not the full size of reality, but just the part available to us. Beyond that, more galaxies, more stars, maybe forever. Some galaxies shoot jets of plasma for millions of light-years. At the heart of many galaxies lies a supermassive black hole. And sometimes, as matter falls toward it, not all of that matter disappears. Some of it gets caught in magnetic fields and blasted outward in narrow, powerful jets. Streams of plasma moving near the speed of light. These jets can stretch far beyond the host galaxy itself, reaching lengths of millions of light-years. We see them glowing in radio wavelengths, forming enormous lows that mark their reach. Galaxies like these are called radio galaxies, and their jets are among the largest structures in the universe. It's a strange irony. The most powerful outflows can come from the regions around black holes, where light can barely escape. Even silence, it seems, can leave a mark. There's a star that orbits the Milky Way backward. Most stars in the Milky Way orbit in the same general direction, following the galaxy's rotation. But not all of them. There's at least one known star named H04375-439 that moves in the opposite direction. Its orbit is retrograde, cutting against the flow like a salmon swimming upstream. How did it get that way? One possibility is that it was part of the smaller galaxy that merged with the Milky Way long ago, and its orbit reflects that older, different system. Or it may have been flung into its current path by a gravitational slingshot, perhaps involving a black hole or dense star cluster. Either way, it's a quiet reminder that not all stars follow the rules. And even in the vast clockwork of the galaxy, there are wanderers going their own way. The center of the galaxy smells like raspberries and rum. It sounds like a joke, but it's real. Astronomers studying the chemical composition of a dust cloud near the center of the Milky Way discovered a molecule called ethyl formate. On Earth, it's associated with the flavor of raspberries and the scent of rum. Of course, the galactic center doesn't actually smell. The vacuum of space wouldn't carry scent the way air does, but the presence of these molecules hints at the complex organic chemistry unfolding in deep space. There are alcohols, sugars, and even amino acid precursors in interstellar clouds. It's not life, but it's the kind of chemistry life might need. So, while space may not smell like fruit and liquor, it contains the building blocks floating silently between the stars. One galaxy is headed straight for the Milky Way, and it's already touching. The Andromeda Galaxy is our nearest large galactic neighbor, and it's on a slow-motion collision course with the Milky Way. Right now, it's about 2.5 million light-years away, but that gap is closing. In about 4 billion years, the two galaxies will begin to merge. And interestingly, the outer halos of both galaxies, their vast clouds of hot gas and dark matter, are already overlapping. So, in a sense, they've begun touching already. The eventual merger will be more of a graceful blending than a crash. Stars will mostly pass by one another without colliding. Over time, the two spirals will become one larger elliptical galaxy. We sometimes call this future system Milka. It's a long wait, but it's already in motion. A cosmic meeting playing out over billions of years. The cosmic microwave background still glows all around you. Every part of the universe, including the space around you right now, is filled with a faint glow called the cosmic microwave background. It's the afterglow of the Big Bang. Light released when the universe was about 380,000 years old. Back then, the cosmos was a hot, dense plasma. When it cooled enough for atoms to form, light was finally free to travel. That light has been moving ever since, stretched into microwaves by the expansion of space. Today, we detect it as a near-uniform glow in all directions. It is not something you can see or touch, but delicate instruments can detect it as a kind of cosmic murmur. This glow is the oldest light we are able to observe, a faint message from the universe's earliest moments, still traveling through space and time. Some supernovae are driven by unseen collapse rather than brilliant light. Supernovae are famous for their intensity, vast explosions that can briefly outshine entire galaxies. Yet not every supernova is bright. Some are known to astronomers as failed supernovae. In these events, the core of a massive star collapses inward to form a black hole, while the outer layers never erupt into a visible explosion. Instead, they may fall inward, feeding the black hole silently. In rare instances, we've watched stars that seemed stable suddenly vanish from view. No explosion, no fading glow, just darkness. These disappearances suggest a collapse so complete that almost all of the energy is swallowed. There's still tremendous violence, but most of it is hidden. It's a reminder that not all cosmic deaths make noise. Some happen in silence. Deep inside gravity's grip, there are entire galaxies made mostly of gas and dark matter. We often picture galaxies as bright spirals or glowing ellipticals filled with billions of stars. But some galaxies are barely visible at all. These dim systems contain very few stars, but they still have mass, mostly in the form of gas and dark matter. They're difficult to detect with regular telescopes and often appear only as faint smudges or through indirect measurements. Some of these galaxies may be failed systems, structures that never formed many stars, perhaps because they were stripped of gas or heated too early in cosmic history. Others may be temporary phases in galactic evolution. What they all have in common is subtlety. No fireworks, no spiraling arms, just quiet gravitational presence. They remind us that not all galaxies shine. Some simply exist. Black holes can collide and merge in cosmic dances. When two black holes orbit one another, they emit ripples in space-time called gravitational waves. As energy leaks away, the black holes spiral inward until they merge in a final, dramatic moment. Two invisible giants becoming one. These collisions don't make light, but they send out bursts of gravitational waves that we can now detect on Earth. The first of these signals was observed in 2015, confirming a century-old prediction by Einstein. Since then, we've detected dozens more. Each one tells a story about massive objects colliding in distant galaxies long ago. These black hole mergers happen quietly, invisibly, but with incredible force, converting entire solar masses of energy into waves that ripple across the universe. And for a moment, the fabric of space itself sings. Some stars die in slow motion, taking billions of years to fade. Not every star ends in a sudden explosion. Smaller stars, like our Sun, die much more slowly. After burning through their hydrogen fuel, they expand into red giants, shedding their outer layers into space. What remains is a dense, hot coal, a white dwarf. This remnant no longer produces energy. It simply radiates away its leftover heat, very, very slowly. A white dwarf can take billions of years to cool, gradually dimming until it becomes invisible. A black dwarf. But the universe isn't old enough for that to have happened yet. Every white dwarf that's ever formed is still glowing somewhere, quietly fading in the dark. The death of these stars is less like a firework and more like an ember cooling gently over cosmic time. Time near a black hole slows down compared to Earth. In Einstein's theory of general relativity, gravity doesn't just pull on matter, it bends space and time. The stronger the gravitational field, the slower time flows relative to areas of weaker gravity. Near a black hole where gravity is extreme, this effect becomes dramatic. If you were to orbit just outside the event horizon, time for you would pass much more slowly than for someone far away. Minutes near the black hole could mean years elsewhere. This isn't science fiction. It's a real, measured effect called gravitational time dilation. We've even observed it in milder form with GPS satellites around black holes. It becomes profound in a way. They don't just trap light, they stretch time itself. The void between galaxies is colder than any lab on Earth. Far from stars, planets, or even gas clouds, the vast spaces between galaxies are astonishingly cold. The temperature there drops to just a few degrees above absolute zero, about 2.7 Kelvin. That's colder than any natural place on Earth, and colder than most environments we can create, even in advanced laboratories. This chill comes from the near total absence of particles and energy. There's nothing to hold heat, just a scattering of stray atoms and the faint microwave glow of the early universe. These intergalactic voids are the quietest, loneliest places we know. Enormous and empty, stretched across millions of light years. They are the universe's deepest shadows, holding only the background whisper of creation. The universe is getting more transparent as it ages. In the early universe, light couldn't travel freely. The cosmos was filled with a hot plasma, a fog of free electrons and atomic nuclei that scattered photons constantly. But as the universe expanded and cooled, it reached a point where electrons combined with nuclei to form neutral atoms. Suddenly, light could move unhindered. This event, called recombination, happened about 380,000 years after the Big Bang, and it released the cosmic microwave background we still detect today. Since then, the universe has continued to grow more transparent. The formation of galaxies and stars added new pockets of light, and as matter spreads out, there's less and less to block a photon's path. With time, the darkness has become clearer. Space, once glowing and opaque, now lets light pass through almost unimpeded. We've captured the shadow of a black hole. In 2019, the Event Horizon Telescope released the first direct image of a black hole, or rather, of its shadow. The black hole itself can't be seen, but the glowing ring of hot gas swirling around it reveals its presence. This particular black hole lives in the center of the galaxy M87, about 53 million light-year away. The image shows a circular silhouette, the region from which no light escapes, surrounded by a halo of radiation twisted by gravity. It took years of global collaboration, coordinating telescopes around the world to act as a single planet-sized lens. The result was more than a picture. It was a quiet triumph of science, giving us our first glimpse at one of the most mysterious objects in the universe. Not through fiction or theory, but through light. You can see a galaxy with your naked eye from your backyard. Most galaxies are so far away that even powerful telescopes reveal only faint smudges. But there's one you can see without any equipment at all: the Andromeda Galaxy. On clear, dark nights in the northern hemisphere, it appears as a soft, hazy oval in the sky, just visible to the eye. It's over 2.5 million light-years away, meaning the light you see began its journey long before humans evolved. Andromeda contains 1 trillion stars, more than double the Milky Way, and it's slowly moving toward us. It's hard to grasp, but you can look up and see an entire galaxy with no telescope, no filter, just the sky, your eyes, and the soft glow of something vast and ancient drifting in the dark. One tiny satellite detected the whisper of a distant black hole collision. In 2015, a small satellite named LIGO detected something extraordinary. A faint ripple in space-time from more than 1 billion light-years away. It was caused by 2 black holes colliding, sending gravitational waves across the cosmos. These waves are incredibly subtle. When they reach Earth, they stretch and squeeze space by less than the width of a proton. Yet with delicate instruments, we can detect them. LIGO and its sister observatories act like cosmic ears, listening to the universe's deepest rumblings. OPA was confirmation of a prediction Einstein made a century earlier, that even in the silence of space, massive events can send out waves. We can feel a single chirp from the merger of invisible giants, caught by a tiny detector on a quiet corner of a small blue planet. Some regions of the universe are expanding away from us forever. The universe is expanding, and that expansion is accelerating as space stretches faster and faster. Some galaxies are being pushed away so rapidly that their light will never reach us. even if we waited forever, the space between us and those galaxies would grow too quickly for the light to close the gap. They've already passed a point of no return, slipping beyond the cosmic event horizon. Eventually, more and more of the universe will fade from view. Not because it's gone, but because its light can no longer reach us. This isn't something we'll feel day to day, but over billions of years, it means the visible universe will shrink. The cosmos isn't just growing, it's also quietly letting go. Some black holes may be primordial, born before stars. Most black holes form from the collapse of massive stars. But there's another possibility: black holes that formed in the earliest moments of the universe before stars even existed. These are called primordial black holes. They may have formed from tiny fluctuations in the dense, hot conditions just after the Big Bang, regions where gravity pulled matter together into ultra-compact knots. Some of these black holes could be incredibly small. Others might have grown over time. We've never directly detected one, but if they exist, they could help explain dark matter, seed the formation of galaxies, or unlock new insights into the early universe. They'd be older than stars, older than galaxies, silent fossils of the first seconds after time began. Entangled particles may link distant corners of the cosmos. Quantum entanglement is one of the strangest phenomena in physics. When two particles are entangled, their properties remain linked no matter how far apart they are. Change one and the other changes instantly, even across vast distances. It doesn't transmit information faster than light, but it does suggest that reality at the quantum level is deeply interconnected. Some physicists think entanglement could play a role in the fabric of space-time itself, maybe even helping to hold space together. In theory, particles created in the early universe could still be entangled today, stretched across the expanding cosmos. If so, there may be quiet, invisible threads connecting distant regions, quantum echoes from the dorm of time, still present in the emptiness between galaxies. The vacuum of space has quantum pressure. Even in perfect vacuum, where there are no atoms, no particles, no radiation, there's still energy. Quantum physics tells us that empty space isn't truly empty. Instead, it's filled with tiny, restless fluctuations, particles and antiparticles appearing and disappearing, fields shifting slightly, always moving. This activity creates pressure known as vacuum energy. On large scales, this pressure may help explain dark energy, the force driving the universe's accelerating expansion. Unlike other kinds of energy, vacuum energy doesn't dilute as space grows. It stays constant, stretching space faster the more there is of it. It's a strange thought that the more nothing you have, the more something it becomes. The quiet force of empty space may be what drives the cosmos apart. Black holes radiate faint heat over trillions of years. Black holes are famously dark, so dense that nothing, not even light, can escape their gravity. But thanks to physicist Stephen Hawking, we know they aren't completely silent. According to quantum theory, black holes can emit a faint glow called Hawking radiation. It happens at the edge of the event horizon, where virtual particle pairs occasionally result in one particle escaping while the other falls in. The escaping particle becomes real, a tiny bit of energy lost from the black hole. Over incredibly long timescales, this slow leakage can cause the black hole to shrink and eventually evaporate completely. For a black hole the mass of the Sun, that process would take more than 1 trillion years. It's the quietest kind of ending, not an explosion, but a long, slow fade into nothing. The universe contains more plasma than solid matter. When we think of matter, we usually imagine solids, liquids, and gases. But the most common state of matter in the universe is something else entirely: plasma. Plasma is an ionized gas, a cloud of particles where electrons and nuclei move freely. It's found in stars, in the solar wind, in interstellar space, and even in the vast regions between galaxies. Most of the visible matter in the universe is in this state. Plasma behaves differently from other forms of matter. It responds to magnetic fields, flows like fluid, and can carry electrical currents across enormous distances. On Earth, we rarely see it outside of lightning, fire, or neon lights. But in space, plasma is everywhere, glowing, flowing, and shaping much of what we see. Even when we don't realize it, gravitational waves travel at the speed of light. Gravity doesn't just pull, it can ripple. When massive objects like black holes or neutron stars collide, they send waves through the fabric of space-time itself. These gravitational waves stretch and squeeze space as they pass, moving outward in all directions. And they travel at the speed of light, the fastest possible speed in the universe. It took decades to develop instruments sensitive enough to detect them. But now we can listen to these cosmic ripples from Earth. Each wave carries information about distant cataclysms, how much mass was involved, how fast the object spun, even how warped space became. Gravitational waves are silent to our ears, but they are real, measurable, and surprisingly gentle. Tiny shutters in the deep structure of the cosmos. The cosmic web connects galaxies across the universe. If you could map the positions of galaxies on the largest possible scale, you'd find something beautiful. A vast, interconnected pattern of filaments and voids called the cosmic web. Galaxies don't sit alone in space. They gather along invisible threads of dark matter and gas, stretching like tendrils between clusters. Where filaments cross, we find superclusters, enormous knots of galaxies. Between them lie immense, quiet voids, almost empty. The cosmic web isn't something we can see with a telescope all at once, but its structure emerges from large surveys of the sky. It resembles a network or a foam, or even the branching patterns of neurons. It's the shape of the universe on its grandest scales, not random, but woven, like something grown rather than built. The James Webb Telescope can see galaxies that no longer exist. The James Webb Space Telescope was built to look farther than ever before, and in doing so, it also looks further back in time. Because light takes time to travel, distant galaxies appear to us as they were billions of years ago. Some of the galaxies Webb observes may no longer exist in the form we see them. They may have merged, faded, or changed entirely. But their light is still arriving, a snapshot frozen in time, still crossing space long after the source has changed. This is one of the quiet oddities of astronomy. Telescopes don't show us what's out there now. They show us what was at different moments across the history of the universe. Every deep field image is also a time machine, a gallery of vanished light. Distant galaxies glow with light that left them before Earth formed. When you look at a galaxy a few billion light years away, you're not just seeing distance, you're seeing age. The light from that galaxy began its journey long before Earth existed, before the Sun formed, before our solar system had even begun to take shape. Some of the galaxies we observe today sent out their light over 10 billion years ago. That glow crossed expanding space, stretched and reened along the way, until it finally reached our telescopes. In a sense, we're watching the universe's ancient past in real time. The stars we see in those galaxies may be long gone. Their light remains a soft reminder that the night sky holds stories older than Earth itself. Entire galaxies can vanish behind clouds of dust. Even something as massive as a galaxy can be hidden by dust. In some regions of space, thick clouds of interstellar dust obscure the light behind them. This dust isn't like the kind you find on a bookshelf. It's made of tiny grains of carbon and silicates drifting through cold molecular clouds. When a galaxy lies behind one of these clouds, much of its light can be blocked in visible wavelengths. We only see it when we look with special instruments in infrared, radio, or X-ray light, which can slip through the dust more easily. Astronomers have uncovered entire galaxies in this way, hidden behind what once appeared to be empty sky. Even in space, appearances can mislead. Darkness does not always signal nothingness. Sometimes it simply means something is waiting to be revealed under the right conditions. Some galaxies are encircled by flawless rings of bent light. In certain cases, a galaxy's gravity warps the light of an object far beyond it. When the alignment is precise, this bending produces what is known as an Einstein ring, a complete circle of distorted light. It is a manifestation of gravitational lensing, where the mass of a foreground galaxy curves spacetime and acts as a lens for light coming from behind it. Einstein rings are uncommon, yet striking. Glowing loops suspended in space, shaped not by motion, but by perspective and gravity. The light can come from a distant galaxy, a quasar, or even a supernova. These rings help astronomers measure the mass of galaxies, map dark matter, and study the early universe. They are silent, perfect illusions, natural lenses created by the shape of space itself. The universe may be infinite. When we look up at the stars, it's natural to wonder if there's a boundary somewhere, an edge to everything. But current observations suggest that space might go on forever. We can only see a finite region, the observable universe. But beyond that, the universe may continue without limit. No edge, no center, just more galaxies, more stars, more space. If that's true, it means that most of the universe will always be beyond our reach. We'll never see all of it, no matter how far we look or how long we wait. An infinite universe doesn't mean infinite possibilities, but it does mean endlessness, a quiet vastness that stretches on gently and without conclusion. Cosmic rays strike Earth from deep space. Every second, high-energy particles called cosmic rays hit our planet. Some from the sun, others from distant parts of the galaxy, or even beyond. They're made of protons, atomic nuclei, and other fragments accelerated to incredible speeds by exploding stars, black holes, or mysterious cosmic forces. Most are deflected by Earth's magnetic field or absorbed by the atmosphere, but some reach the surface, and a few even pass through you. These particles are mostly harmless in small doses, but they are a required reminder that space is not empty. It's alive with motion, energy, and invisible messengers from far-off events. Every now and then, a cosmic ray hits a detector and tells a story that began light years away. A particle's journey from a supernova to your sky. There may be no such thing as before the Big Bang. The phrase before the Big Bang seems natural, but it may not make sense. According to general relativity and many cosmological models, time itself began with the Big Bang. That moment wasn't just the birth of matter and energy. It was also the beginning of space and time as we know them. Asking what came before is a bit like asking what's north of the North Pole. Some theories suggest a previous state or universe, while others describe a quantum realm where time behaves differently or doesn't exist at all. But in most models, before the Big Bang isn't a place we can visit, even in thought. The Big Bang wasn't an explosion in space. It was the beginning of space. Astronomers once mistook quasars for nearby stars. When quasars were first discovered, they looked like faint, point-like objects, almost identical to ordinary stars. But their light didn't behave the way it should. Their spectra were strange, and their brightness varied in puzzling ways. It took years to realize that these weren't stars at all. They were distant galaxies with incredibly active centers. A quasar is powered by a supermassive black hole, surrounded by a swirling disk of hot, falling gas. That gas heats up and glows with unbelievable intensity, sometimes outshining the rest of the galaxy combined. The first quasars were so far away that their light had traveled billions of years to reach us. And yet they looked like tiny stars, a case of mistaken identity that turned out to be one of the brightest discoveries in astronomy. Our local group of galaxies is falling toward a hidden region. The Milky Way doesn't sit still. Along with the Andromeda Galaxy and dozens of smaller companions, it drifts through space as part of a loose collection called the local group. And this group, in turn, is moving towards something larger, a gravitational anomaly called the Great Attractor. But beyond even that lies a more mysterious region, the Shapley supercluster, and perhaps others still hidden by the dense plane of our galaxy. These distant masses exert a pull we can measure, even though we can't yet see all of them. It's as if our entire neighborhood is sliding towards something enormous, wrapped in shadows. We don't know what lies in that direction, only that we're moving toward it slowly, pulled by the weight of unseen giants. We are living in the universe's stellar springtime. Right now, the universe is filled with stars, burning, forming, exploding. But this is a relatively recent development. For the first few 100 million years after the Big Bang, there were no stars at all. The first ones formed in darkness, lit up their surroundings, and began the process of cosmic evolution. Since then, star formation has risen, peaked, and slowly declined. We now live in what might be called a cosmic spring, a time when new stars still form, but less than before, and much more than will come in the far future. One day, the last stars will be born, and after that, the universe will slowly darken. But for now, it is still alight with new beginnings, bright enough to wonder, quiet enough to rest. In the distant future, stars will stop being born. Star formation depends on cold gas, clouds of hydrogen and helium that collapse under gravity. But over time, this fuel becomes scarce. It gets locked up in stars, blown away by supernova, or heated beyond usefulness. Billions of years from now, galaxies will run out of the material needed to form new stars. The ones that remain will age, burn out, and fade away. First the blue giants, then the suns, then the red dwarfs, until even the slowest burning embers cool into blackness. The universe won't end all at once. It will dim by degrees, quietly and gently. What's left will be black holes, white dwarfs, neutron stars, and the silence of a cosmos grown cold. Not tragic, just still. Most matter in the universe is invisible. When we look at the universe, stars, galaxies, nebula, we're only seeing a small fraction of what's really there. Most of the matter in the cosmos doesn't shine. It doesn't emit or reflect light. This invisible substance is called dark matter. And although we've never detected it directly, we know it exists because of its gravitational effects. Galaxies spin faster than they should. Light from distant objects bends more than expected. Clusters hold together with more strength than their visible mass allows. All of this suggests a hidden mass, more than 5 times the amount of ordinary matter. Dark matter is everywhere, shaping the structure of the universe. We just can't see it. It's a quiet, invisible framework holding everything else in place. Light from the first galaxies has been stretched by cosmic expansion. When light travels through space, it doesn't just move, it stretches. That's because the universe itself is expanding. And as it grows, it pulls light waves along with it. The light that left the first galaxies billions of years ago has been stretched into longer wavelengths, moving from visible light into the infrared. This process is called redshift, and it's one of the main ways astronomers measure distance and time in the universe. The more stretched the light, the farther and older its source. With telescopes like James Webb, we can finally see that ancient light, now softened and reddened by the journey. What began as the glow of young stars now arrives as a whisper stretched by the breath of space itself. The universe may be a hologram. It sounds like science fiction, but some physicists have seriously explored the idea that our three-dimensional universe might be a projection from a deeper two-dimensional reality. This is known as the holographic principle. It comes from studies of black holes, where information about everything that falls in seems to be encoded on the surface, not the volume of the black hole itself. Some theories suggest that the universe as a whole might work the same way. What we perceive as space and depth could be a kind of mathematical illusion arising from information encoded on a distant boundary. It's not proven and probably won't affect your day-to-day life, but it's a gentle reminder that reality, even at its most solid, may not be quite what it seems. Space may be granular at the smallest scale. To the naked eye, space appears smooth. Even under a microscope, it's still empty and continuous. But some theories of quantum gravity suggest that space itself may be made of tiny, discrete units, like grains or pixels in a digital image. This smallest possible scale is called the Planck length, about 10 to the power of minus 35 meters. At that level, smoothness may break down into something more fundamental, a grainy, foamy texture of space-time itself. We don't yet have the tools to see it or even to test it directly. But if it's true, then everything, stars, galaxies, thoughts, even sleep, happens not in a perfect void, but in a universe with structure all the way down. There are stars that spin faster than kitchen blenders. Some stars rotate so rapidly that their equators bulge outward and their surfaces blur into a speeding blur. Neutron stars, the dense remnants of massive stars, take this even further. A type called a millisecond pulsar can spin hundreds of times per second. That means the entire star, a city-sized sphere of nuclear matter, rotates faster than a blender blade. These objects emit beams of radiation that sweep across the sky like cosmic lighthouses, ticking with astonishing precision. Many of them are locked in tight orbits with companion stars, pulling in matter and gaining speed. They are some of the fastest known rotators in the universe, and also some of the oldest clocks, ticking silently in the night. The universe could end in a slow, quiet fade. Cosmologists once wondered if the universe would collapse back in on itself, but the evidence now suggests a different fate: slow, endless expansion. As galaxies drift farther apart and star formation slows, the night sky will grow darker. Existing stars will burn out one by one. Black holes will evaporate. Matter itself may decay, and the universe will become colder, quieter, and emptier. A state called heat death. It's not a sudden event, but a long, gentle fade. Over trillions of years, the cosmos will grow still as energy spreads thin and structures dissolve. It's not the end as fire or ice, but as silence, a universe that whispered itself into being and eventually whispered itself away. Some galaxies have super winds that blow away stars. At the heart of some galaxies, especially those with active black holes or intense star formation, powerful winds can blow out from the center, carrying gas, dust, and even young stars with them. These galactic superwinds can stretch for tens of thousands of light years, pushing material into intergalactic space. They are driven by radiation, magnetic fields, and the explosive energy of supernova. Over time, these winds can strip a galaxy of its star-forming gas, leaving it quiet and red. They also help spread heavy elements into the cosmic web, seeding future generations of stars and planets. In this way, a galaxy breathes, taking in matter, igniting life, and then exhaling into the void. The far future of the cosmos is an endless, dark ocean. Trillions of years from now, the universe will look very different. Galaxies will have drifted apart so far that each one will seem alone in the dark. New stars will stop forming. Old stars will burn out. Even the faint glow of white dwarfs will fade. What remains will be cold, scattered remnants, black holes, and the thin echo of ancient light. Over unimaginably long timescales, black holes will evaporate, and even matter itself may decay. Eventually, all that remains will be particles moving through empty space, silent, slow, and alone. This future is called the heat death of the universe. But it's not a sudden end. It's a vast, dark stillness, a cosmic ocean with no waves, no wind, and no shore. We might be living inside a giant cosmic void. The universe is filled with clusters of galaxies, and between them, enormous empty regions called voids. These voids span hundreds of millions of light years and contain very little matter. Some researchers believe we may be inside one of these voids right now, a relatively underdense region compared to the average cosmic background. If true, it could help explain certain observations, like the expansion rate of the universe or patterns in the cosmic microwave background. Living within a void does not affect daily life, but it suggests that what feels like emptiness may be part of a much larger pattern, the calm center of a cosmic bubble, slowly drifting through a lattice of unseen gravity. Magnetars possess magnetic fields trillions of times stronger than Earth's. A magnetar is a kind of neutron star, the city-sized remnant of a collapsed star, carrying a magnetic field of almost unimaginable power. Earth's magnetic field is strong enough to steer a compass. A magnetar's field is so intense it could wipe data from thousands of miles away, distort atomic structures, or rip matter apart. These fields do not last forever, They weaken over time, but while they persist, they unleash flares and bursts of extremely high-energy radiation. A single magnetar flare, even from the far side of the galaxy, can still be detected here on Earth. No lab could create such intensity. They're among the most extreme objects in the universe. Dense, silent, and wrapped in invisible force, like stars that have become nothing but memory and magnetism. The universe's largest known object is a giant quasar group. In 2013, astronomers discovered a vast structure made up of quasars, the luminous cores of distant active galaxies stretching over 4 billion light-years across. This structure, called a large quasar group, is so big it challenges our understanding of cosmic uniformity. According to current theory, the universe should be relatively smooth on the largest scales, with no structures exceeding a certain size. But this quasar group is larger than that theoretical limit. It's made of dozens of quasars, connected across an enormous stretch of space, suggesting that the early universe may have formed larger patterns than we once thought. Whether it's a true physical structure or a statistical fluke is still debated. Either way, it reminds us that the universe is more complex and perhaps more connected than our models can always predict. Black holes can twist space into a funnel of time. A black hole doesn't just trap light, it warps space-time itself. As you approach its event horizon, space bends inward and time slows down. To an outside observer, time near the black hole appears to crawl. At the very edge, it almost stops. This warping creates something like a funnel in the geometry of space. Narrow, steep, and one way. Inside, all paths lead toward the center, the singularity. The closer you get, the more time and space seem to trade places, with inward becoming a direction in time, not space. You can't go back. This twisting of space-time is more than metaphor. It's geometry drawn by gravity written in the fabric of reality itself. Some regions of the universe may never see each other again. Because the universe is expanding and accelerating, some parts of it are already moving apart faster than light can travel. This means that even if we wait forever, the light from those regions will never reach us. The same is true in reverse. There are places we can never send a message to, because the space in between is stretching too quickly. Over time, more and more of the universe will slip beyond reach. Each galaxy will become an island, isolated in space, surrounded by darkness. This doesn't break the laws of physics. Nothing is moving through space faster than light. But space itself can grow calmly and unstoppably, separating one piece of the cosmos from another forever. The heaviest element made in a star explosion is gold. Gold is rare on Earth, not just in our economy, but in the universe itself. It can't be made in the core of an ordinary star. Instead, it forms in the most extreme events, the collisions of neutron stars or certain kinds of supernova. In those moments, atomic nuclei are smashed together under incredible pressure and heat, creating heavy elements like gold, platinum, and uranium. These precious atoms are then scattered into space, mixed into gas clouds, and eventually become part of new stars, planets, and people. Every gold ring, every fleck of dust was born in a cosmic catastrophe. A quiet trace of violence, now resting on your hand. In that sense, gold is not just beautiful, It's ancient. It's stellar. And it came from a universe that forges treasure in fire. The space between galaxies expands while light travels through it. When we observe light from distant galaxies, we're seeing it as it was long ago, but also stretched by the space it moved through. As the universe expands, so does the distance the light has to travel. And that means the light itself is stretched. Its wavelength lengthens, shifting toward the red. This is called cosmological redshift. The light isn't slowing down or losing energy by hitting things. The space it moves through is simply getting bigger. In effect, the universe stretches the signal on its way to us. When we see faraway galaxies, we're seeing more than age or distance. We're seeing how space has changed since the moment that light began its journey, a silent record of the universe's steady breathing. There are sound waves frozen into the structure of the cosmos. In the early universe, before atoms formed and light could travel freely, matter and energy were tightly coupled in a hot plasma. In that plasma, pressure and gravity created oscillations, ripples of compression and rarefaction like sound waves in air. These acoustic waves left an imprint in the density of matter, a kind of frozen echo. Today we can see that echo in the distribution of galaxies, a preferred distance between galaxy pairs, like a standing wave preserved in space. This phenomenon is known as baryon acoustic oscillation. It's subtle but measurable, a fossil record of cosmic sound winging out from a time before the universe became transparent. A wave that never fades, quietly shaping the structure of everything we see. Galaxies can be eaten by larger ones without a trace. In the vast timescales of cosmic evolution, galaxies don't just float alone. They interact, collide, and sometimes devour each other. When a small galaxy comes too close to a larger one, gravity can tear it apart. Its stars are pulled into long streams, absorbed into the larger galaxy's halo, and eventually blended so thoroughly that the smaller system vanishes from view. We found remnants of such mergers around the Milky Way. Stellar streams arcing through the sky, once part of other galaxies. This process is called galactic cannibalism, but it's slow and elegant, not violent, just inevitable. Over time, large galaxies grow this way, not through building, but through quiet consumption. One galaxy absorbed into another, leaving only a ripple in the stars. There are stars that flicker like fireflies in the night. Not all stars shine with steady light. Some pulse, shimmer, or dim, and brighten in rhythmic patterns. These variable stars change for many reasons: internal pressure waves, surface eruptions, or eclipsing companions. From Earth, they look like they're flickering gently in the sky, blinking with a slow, stellar rhythm. Some complete their cycle in hours, others in years. These variations aren't random. Many are remarkably consistent, acting like celestial clocks. Astronomers use them to measure distances across the universe. A single flicker, repeated over and over, can tell us how far away a star is, and even how bright it truly is. Stars don't just burn, some of them breathe. Some black holes wander through space alone. Not all black holes live in the centers of galaxies. Some roam. A black hole can be ejected from its birthplace by gravitational interactions, kicked out of a galaxy during a collision, or flung away by the recoil of a merger. Once released, it becomes a rogue object, moving silently through interstellar or even intergalactic space. These wandering black holes are hard to detect. They emit no light unless they pass through gas or pull on nearby stars. But they're likely out there, drifting through darkness, unseen and unbound. They carry no orbit, no companion, no home. Just mass, motion, and the deep gravity of the thing that fell inward and never stopped falling. Even black holes can get kicked across the galaxy. When two black holes merge, the violent event sends out a burst of gravitational waves. But those waves aren't always symmetrical. If the merger sends more energy in one direction, it can give the new black hole a kind of recoil, a gravitational kick strong enough to hurl it away at thousands of kilometers per second. Some black holes may be flung entirely out of their galaxies, doomed to drift through intergalactic space. Others settle into wide, wandering orbits. These kicked black holes are hard to spot, but astronomers believe they exist. Silent travelers pushed by the memory of their own collision. Even the heaviest, most anchored things in the universe can be moved by the right kind of wave. Some stars are stripped down to bare cores of pale carbon. When the star, like our Sun, dies, it sheds its outer layers and leaves behind a core, a white dwarf. Some white dwarfs are made mostly of carbon, and under the immense pressure of their own gravity, that carbon may crystallize. In other words, some stars become giant diamonds. These stellar diamonds are about the size of Earth, but far heavier, glowing faintly with leftover heat. They no longer fuse atoms, but they still shine for billions of years before cooling to blackness. Astronomers have even detected pulsations in some white dwarfs, a kind of ringing, like the sound of a struck bell. A silent, cooling jewel floating in space. Once a star, now a crystal of ancient fire. Most of the universe's history hasn't happened yet. 13.8 billion years sounds like a long time. But if you imagine the entire future of the universe, not just tomorrow or a million years from now, but trillions of years into the future, we're still near the very beginning. Stars are still forming, galaxies are still assembling, black holes still shine with the heat of falling matter. In the far future, the stars will fade, the galaxies will drift apart, and the universe will grow cold and quiet. But that chapter hasn't begun yet. Right now, we live in a moment of light, a brief golden season when the cosmos is alive with motion and change. The past is vast, but the future is bigger still. Supernova remnants keep expanding for thousands of years. When a massive star dies, it goes out in a supernova, a brilliant explosion that can briefly outshine an entire galaxy. But the event doesn't end with the flash. The shockwave expands outward for centuries or even millennia, sweeping up gas, dust, and anything in its path. These expanding shells of debris are called supernova remnants. They glow in many wavelengths: radio, X-ray, visible light, and their patterns tell the story of the explosion. Some form delicate filaments, others turbulent clouds. The Crab Nebula is one such remnant, still spreading outward from a blast that was seen on Earth in the year 154. Supernova remnants are the slow exhalations of dead stars, still unfolding long after the light has faded. A light from a distant star can be twisted by a single planet. We usually think of gravity bending light on a massive scale, by stars, black holes, or galaxies. But even a planet can do it. If a planet passes directly between a distant star and Earth, it can act as a tiny gravitational lens, magnifying and distorting the starlight. This effect is called microlensing. It's subtle and rare, but powerful enough to reveal planets we could never see otherwise, even in other galaxies. A flicker in the light, a gentle curve in the brightness, and suddenly a world is revealed. The planet itself might be cold, dark, and invisible, but its presence twists the starlight ever so slightly. And that twist is enough to say, "I'm here." The universe once glowed with a brilliant orange light. In the early days after the Big Bang, the universe was a hot, dense plasma glowing with intense light. But as it expanded and cooled, that glow shifted. When the temperature dropped to around 3000 Kelvin, the first atoms formed and light could travel freely. At that moment, the universe would have looked orange, not the blue-black of night we see now, but a soft, warm radiance filling all of space. This light has since been stretched by the expansion of the universe into the faint microwave glow we detect today, the cosmic microwave background. But long ago, there was a time when the entire cosmos glowed orange, as if lit from within, a quiet ember fading into time. Some parts of the universe are cooling slower than others. As the universe expands, it cools gradually, gently, like a vast oven being turned off. But not every region cools at the same rate. Some regions, packed with greater amounts of matter or trapped radiation, hold on to heat for much longer. Galaxy clusters, for instance, contain vast reservoirs of hot gas that can stay warm for billions of years. Other areas are more isolated and lose heat far more quickly. These temperature contrasts influence how structures take shape, how stars develop, and how long certain cosmic processes can continue. Even in a universe guided by simple laws, local differences emerge. Warmer pockets, slower cooling, brief pauses in the grand progression. The universe does not cool like a machine. It cools more like weather, uneven, layered, and quietly dynamic. One day, we may even witness the birth of a new universe. Some cosmological theories propose that new universes could arise within our own, branching off through quantum fluctuations, black holes, or other processes we have yet to fully understand. If this happens, it would likely occur far from us, beyond any observational reach. But in theory, it might be possible to witness the signs, a sudden expanding bubble of new physics tearing away from our familiar reality. We don't know if this has ever happened. We don't know if it ever will. But the idea remains that somewhere, someday, the quiet darkness of our universe could give birth to something new. A beginning inside an ending, a whisper inside a silence. The cosmos is still ringing from its earliest moments. In the first fraction of a second after the Big Bang, the universe expanded explosively, an event known as inflation. That burst of motion left behind ripples, tiny quantum fluctuations stretched across space. These ripples became the seeds of all future structure, galaxies, stars, planets, and they also left behind echoes. We see them in the cosmic microwave background as temperature variations, and we may one day detect them as primordial gravitational waves, faint rhythmic pulses in the fabric of space-time itself. The universe may seem quiet now, but it still carries the memory of that first vibration, like a bell still humming softly long after the strike. The universe is vast, and you are a way for it to know itself. Of all the strange facts in astronomy, perhaps the most quietly astonishing is this. You are made of stardust. The carbon in your body, the calcium in your bones, the iron in your blood, all were forged in stars, scattered across space, and gathered into life. You are not separate from the cosmos. You are a moment of it made conscious, a flicker of awareness in a universe that otherwise only moves and burns and cools. In this sense, the universe has grown eyes, and through those eyes, it looks back at itself, wonders at itself, dreams of itself. And even now, as you drift towards sleep, it keeps dreaming. Thank you for spending this time here, floating through the cosmos with me. We've cliffed across vast distances, past dying stars and newborn galaxies, listening to ripples in space-time and echoes from the earliest moments of creation. And somewhere in all of it, in the light of ancient stars, in the silence between galaxies, in the quiet shimmer of dust, there was you, breathing slowly, thoughts softening, maybe even already asleep. This universe is full of motion and mystery, but also stillness. It holds heat and light and gravity, but it also holds peace. And the fact that we can know it piece by piece, in calm and in quiet, is something truly beautiful. So wherever you are now, whether you're fully awake or drifting beyond the edge of thought, may your dreams tonight be gentle. May your body rest like starlight on water, and may you carry with you, even faintly, the memory of a universe that glows, not just above you, but within you. If you happen to still be awake, you can go ahead and watch the next chapter now. And if you'd like to drift off to more stories like this, softly told, filled with wonder, consider subscribing. There's always more to explore, one sleepy soul at a time. Good night.